Yes, am I audible?
Yes, sir.
Okay. So
Good
in
evening, sir.
good evening. So in the last class, we have finished some applications of Ampere's circuital law. We started this solenoid. What is solenoid, Saifullah?
It's a wire with multiple loops.
Wire with multiple loops. And what are the approximations for a long solenoid, Saifullah? What are the approximations that we can use from a long solenoid?
A magnetic field is uniform. Gives the same magnetic field as a bar magnet.
And magnetic field outside the solenoid is 0. Right? These are the two approximations. That magnetic field, when we use a long solenoid, then we use two approximation. One is magnetic field is uniform in the central region of the solenoid, and magnetic field outside the solenoid is 0. There's no magnetic field outside the solenoid. So Sahil, is your first lecture with me. I'm just finishing Ampere's circuital law. After Ampere's circuital law, I will start Lorentz force. Lorentz force is a fresh topic. So just wait for 10-15 minutes. In the 10-15 minutes, we'll finish this application of Ampere's circuital law, and we will start Lorentz law. From Lorentz law, you can follow easily. Okay, so this is a solenoid. Current going inwards and coming outwards. I take this cross-sectional view of the solenoid, means I cut this solenoid. So when you cut this solenoid, this is outwards, this is inwards, and current is going like this. Current is coming out of the plane, then it's going inwards, out of the plane, inwards. Just let me show you just give me 1 second now. I'm showing you an animation for the solenoid so that I can explain it better.
Take a long coil with many circular turns of insulated copper wrapped closely in the shape of a cylinder. This type of coil is called as a solenoid. The electromagnetic effect of a solenoid is used in several appliances. Let us pass electric current through the solenoid and observe the pattern of magnetic field lines demonstrated here.
Just 1 second. Yeah, this is a typical solenoid. This is a solenoid. So current is flowing through this solenoid. It's coming outward, then it's going inwards, then current will come out, current will go in. This is how the current is flowing in the solenoid. So there are two ways to draw this solenoid. One is this one, and another is the cross-sectional view. In the cross-sectional view, what we can do is we can cut the solenoid from here. We can cut this thing from here. We'll cut this solenoid from here. So from one end, you can see that current is coming outwards. At the other end, you can see that current is going inwards. Yes, is it clear? The figure of the solenoid? We can start the calculations if this thing is clear.
Yes, sir.
Yes, sir.
One end current is going outwards, another end it's inwards, and it will come out, then it will go inwards and so on. We take the cross-sectional view, the current is coming outwards and it's going inwards, coming outwards, inwards, outwards, inwards, inwards. So what we do is to calculate, then we define few quantities. I is current through each turn of the solenoid. Capital N, small n is number of turns per unit length. Then we will calculate. Okay. So I is current through each turn, n is number of turns per unit length. So to calculate magnetic field using Ampere's circuital law, what were the steps, Arpit? What was the first step in calculating magnetic field using Ampere's circuital law?
So we used to consider an Amperian loop.
Arpit, you are not audible.
Sir, now also.
Nabil Ahmed, what was the first step in calculating
Sir,
magnetic? Yes,
I was not audible.
you are audible now.
Sir, I was saying that first we have to identify the Amperian loop.
Okay, good. So we will consider an imperial loop. Consider a square imperial loop. We will consider a square imperial loop. Of each
Sir?
side, yes.
Sir, but in this criteria, sir, we studied that we will consider it as circular only.
No, for a straight conductor or a cylindrical conductor, we will consider a circular loop. But it's not a straight or a circular conductor. Not a,
Oh,
it's
okay,
neither
sir,
a straight nor a cylindrical conductor. So consider a square loop. This is the name of the loop. This is A, B, C, D. We take this loop. Name of the loop is A, B, C, D. That's the first step. What is the second step, Mehraj? When we calculate magnetic field using Ampere's circuital law, what is the second step? The first step is we consider a square Amperian loop and each side is L. The name of the loop is ABCD. What is the second step?
We apply closed integral of B dot dl.
We use Ampere's circuital law. We use and the Ampere's circuital law says closed integral of B dot dl is mu naught I. That's first equation. Then we will solve. No, this integral is over the entire loop ABCD. Now we'll solve this integral like closed integral of B dot dl over the entire loop. The name of the loop is ABCD. So when we solve this integral, this is first we take integral from A to B. So see, this is the loop ABCD. When we solve this integral, we'll solve this integral for each part individually. Like first we will solve it from A to B. Then we will solve it from B to C, then C to D, and then D to A. This is A to B, B dot dl, plus it's B to C, B dot dl, plus it's C to D, B dot dl, plus it's D to A, B dot dl. So we solve for each of the individual parts. Now, when we consider the integral from A to B, see your magnetic field is along x-axis. We take a small dl element here. The direction of length element is also along x-axis. So the angle between magnetic field and dl element is 0 degree. So we can solve it as A to B. It's B dl cos 0. See, this is the direction of the imperial loop. This arrow, it's anti-clockwise. I take imperial loop as anti-clockwise. So when we integrate it from A to B, this is the small integral dl, small length dl. B and dl are acting in same direction. So the angle between them is 0 degrees. So it's A to B, B dl cos 0. B to C. B and dl are perpendicular to each other. B to C is the direction of dl and this is the direction of magnetic field. Magnetic field is perpendicular to the length element. So it's B dl cos 90. C to D. This C to D portion is outside the solenoid. Outside the solenoid, magnetic field is 0. So this integral is also 0. Then we solve it from D to A. So when we go from D to A, then magnetic field and dl element are perpendicular. D to A is B dl cos 90. This is 0, this is 0, and this is A to B, it's B dl. So we take B outside the integral. This is A to B, it's integral of B. So when we integrate this thing from A to B, we get length element L. So this comes out to be B. Let's call this as equation. So the closed integral of B dot dl is BL now. The next step is we need I enclosed. So see, what is I here? I is current through each turn. Now, if you take this imperial loop, can you count the number of turns passing through the imperial loop, Akshay? Akshay.
So 2.
Yes, sir.
If I consider this imperial loop, then there are only 2 turns. But this 2 is just a reference. I can draw as many turns as I want. So mathematically, what we can do is we can represent the number of turns in this length L. See, the small n is the number of turns per unit length. In unit length, the number of turns are small n. So what about the number of turns in length L? See, the length of the imperial loop is L. I have to count the number of turns in length L. In unit length, you have small n turns. So number of turns in length L. The number of turns in length L is NL. So your I enclosed would be, see, current passing through a single turn is I. You need current which pass through this NL turns. So your I enclosed will be NLI. This is equation number 3. Now we can substitute this 2 and 3 in 1. So when we substitute 2 and 3 in 1, instead of this B dot dl, I can substitute B into L, which is equal to mu naught. Instead of this I enclosed, I can substitute NLI. L will cancel this L. And I get that magnetic field is, it's mu naught Ni. This is the magnetic field, B is mu naught Ni for the solenoid. But before using this expression, you should remember 2 approximations. The first one is, this is valid only for long solenoid. Valid only for a long solenoid. Second, this is in central region. This is at the center of solenoid. This expression is valid only for the central region of the solenoid. Next. See, till now, the core of the solenoid means this region is air. We wound the wires over air only. If we take any other core, if core of solenoid is of material having relative permeability mu1. Having relative permeability mu1. Then you can write that your magnetic field is mu naught, mu r, and I. We'll just multiply this mu naught with the relative permeability of the beam. Core is something else, means in between the turns, if you place some other material, like if you place some iron slab or something, then your magnetic field will be mu naught mu r into N. And just one last thing. If instead of center, you're supposed to calculate, if you want to calculate magnetic field at the ends of the solenoid, then at the ends of the solenoid, magnetic field is just half of the center. See, we can't derive this expression using Ampere's circuital law. We derive this expression using Biot-Savart's law, but it's not a part of syllabus, so I'm not deriving it here. But you should remember, at the center, magnetic field is mu naught Ni. At the ends, it will be mu naught Ni, right? Note it down. Please do it faster. Just one more small calculation, then this Ampere circuital law is over. Then we will start Lorentz force. Miraj, clear?
So,
Yes.
so can you explain again, sir, how we got I enclosed?
I enclosed. Okay, just note it down. I will explain it again when you come to this thing. Just note down this part of B dot dl. I'll explain it. Yes, yes, Akshay. So, you are asking about I enclosed, na? See, the
Yes.
current through each turn is I, and this ABCD is your Amperian loop. Huh? So, through
Yes,
this
sir.
Amperian loop, 3 turns are passing. So, current
Yes,
should
sir.
be 3I, right?
But sir, like it could be any number, right?
It could be any number. That's why we take a number which is small n. Small n is number of turns per unit length. Means through 1 meter of the wire, the number of turns are small n. The length of the wire is L. Then how many turns are in this length L?
NL.
NL. So that you can write here, no? NL. So I number of turns is NL and current through one turn is I. So current through NL turns will be NLI. Clear now?
Yes, sir. Got it.
Akshay, I have written that, drawn that figure.
Yes, sir.
Minashi, doubt in any step?
No, sir.
Noha, Yashika,
No, sir. No, sir.
Manshika, doubt?
No, sir.
Yes, can I scroll it now?
सर वो सी से डी वाला 90 क्यों है?
CCD, because this is outside the solenoid. Na? This point is outside the solenoid. C to D.
Okay.
And outside the solenoid, magnetic field is here.
सर अगर हम आई एनक्लोज को NLI लिख रहे हैं तो फिर उसका यूनिट चेंज नहीं हो जाएगा करंट?
No, because N is number of turns per unit length and this is length. So meter inverse and meter. Number of turns have no unit. This is meter inverse. M is meter and M is. Okay.
Yes.
So the value of mu r will vary material to
Yes,
material.
yes. Value of mu r is different for different materials. It's maximum for ferromagnetic material. For example, iron, the mu r is around 1000. Yes, written.
Yes, sir.
1 minute, sir.
See, you will not get many numericals from solenoid from chapter number 4. Solenoid is mostly used in chapter number 6. So the major numericals in solenoids are in chapter number 6 only. In chapter number 4, you usually get derivation of solenoid. The numericals are in chapter number 6. Basically, we combine solenoid with Lorentz force, or we combine solenoid with self-induction. Then you get good numericals.
Sir, bends made at the end of the solenoid.
Sorry? Yes, that's ends of the solenoid. Not bends, it's B ends. Magnetic field at the ends. B stands for magnetic field at the ends of the solenoid.
सर relative permeability question में given है.
Yes, given only. जैसे डायलेक्ट्रिक कांस्टेंट गिवन होता है ऐसी ये गिवन. अंशिका, written.
That's mu naught Ni by 2.
Yeah, mu naught Ni by 2. Just half of the magnetic field at the center.
Okay.
Anshika, written.
Yes, sir.
So देखिए, let's see. The next is toroid. Toroid is a circular solenoid. The number of turns are wound over a circular core. You can consider it like this. These number of turns are over a circular core. So this is a toroid. Some current I is entering into it. Then the same current I will come out of. This is a toroid. If you want to draw the cross-sectional view of the toroid, that means you will cut this toroid. You will cut this thing. When you cut this toroid, it will look like this. You will see the inner radius. Then you can see the outer radius. And current will come out of this. It will come out. Then it will go in. Current will come out. And then current will go in. It will come out and then it will go in. See, this is the wires. The current is coming out of the wire, it's going into the wire. Current is coming out of the wire, then it's going into the wire. These are the wires through which current is flowing. Then it's again outwards, inwards. Outwards, inwards. This is the inner radius of the toroid A. This is the outer radius of the toroid B. In this figure, this is the inner radius A, and this is the outer radius B. This is the toroid. Now, in this toroid, we can calculate magnetic field in 3 regions. See, this is region number 1. Here we can calculate magnetic field. Region 2, here we can calculate magnetic field. And this is region 3, we can calculate magnetic field here. So first of all, let's calculate magnetic field in region 1. This is region 1. The radius is R. So in region 1 means R is less than A. This region inside. So Anshika, what should be the value of I enclosed in region 1? Anshika, this is the region 1, huh? And this is your loop. I take loop here. What is the current enclosed by this loop, Anshika?
Sir,
I current. Anshika, current is flowing through these wires, huh? I'm asking current here. What is current passing through this loop, this circular loop? Nabil Ahmed.
Sir, 0.
0. Why?
Because there's no current flowing through. There's no wires inside.
Yeah, there's no wires inside. Now wires comes here, then it goes here. Wire is in this region only. There's no wire here. Anshika, so what should be the I enclosed in region 1?
Sir, 0.
And what should be the magnetic field here?
Sir, 0.
So in region 1, there is no magnet. Then we take region 2. In region 2, R is greater than A, but it's less than B. So region 2 is this one. If you want to see region 2 in this figure, this is region 2. So I take it here. So what are the yes?
Less than B or more than B?
Less than B. It's greater than A. This is A. It's greater than A and less than B. Greater than A and less than B. So we take a imperial loop. Of radius R. Now let's apply Ampere circuit. B dot dl is mu naught I enclosed. That's first equation. Now when we calculate B dot dl, say it's a circular loop. What is B dot dl for a circular loop, Yashika? You have calculated this
2 pi r.
B into 2 pi r. That is B dot dl for a circular loop. It's B into 2 pi r. If I take n, capital N are the number of turns, and I is current through each turn. Rishika, this is the imperial loop, huh? Not Rishika. Noha. Noha, this is the imperial loop. How much current is enclosed by the loop? Noha. This loop have n number of turns. How much current is enclosed by the loop? Noha.
Sir, NMI.
Ni. See, this is 1, 2, 3, 4, 5, n turns. Current through each turn is I. So the current enclosed by this loop is Ni. So you can say that I enclosed is Ni. Let's call this as equation number 3. Next, what we can do is we can just substitute the values here. We can substitute 2 and 3 in 1. So when we substitute 2 and 3 in 1, we will get the value of magnetic field in region 2. So let's substitute 2 and 3 in 1. Mehraj, how much is B dot dl? B into 2 pi r. I enclosed is Ni. So instead of this I enclosed, I will substitute Ni. It's mu naught Ni. So your B will comes out to be, it's mu naught Ni by 2 pi r. This is magnetic field in region 2. There's some more calculations that we can do here. Nabil Khan, what is the length of the toroid? See, this is the toroid, inner radius A, outer radius B. What is the total length of the toroid? Nabil Khan, radius, inner and outer radius are given. I'm asking about the total length of the toroid. What is the total length?
B 2 pi into B minus A.
2 pi into
B minus A.
minus A, no. So the total length is not 2 pi. 2 pi into B minus A means this thing. The total length is the circumference.
N into 2 pi into B minus A, sir. Because number of turns.
B minus A will give this region only. Huh? So the total length
pi
is
r.
this. 2 pi r. What is which r? A or B?
Sir,
B.
B.
Because when you take A, the length will be different.
Yeah.
The length will be the circumference. And when you
2
take
pi
B,
b.
length is different. 2 pi A or 2 pi B. So what we do is, see, you can see that if I take the inner radius, then it's 2 pi A. If I take the outer radius, it's 2 pi B. What we can do is we can take an average radius. Let's take an average radius.
2 pi a minus 2 pi b.
No. How we take average, it's A plus B by 2. See, when you take B minus A, then you are getting this length. This one. You don't need this length. You need this whole circle.
Sir, but average means it will be through midpoint, right?
Average means
It will be
somewhere in between. So if I take the average radius, say if inner radius is 2, outer radius is 4, then average radius is 3. So this much is 3. Then you will get this length. So I'm taking average radius A plus B by 2. I'm calling 2 pi r as the average length of solenoid. Average length of toroid. So what will be n by 2 pi r? See, n is total number of turns and 2 pi r is roughly the length of the toroid. So total number of turns divided by length is represented by small n. Small n means number of turns per unit length. Per unit length. If I call this as equation number 4, I call this as equation number 5. And if I try to substitute 5 and 4, then see what you will get. So when I substitute 5 in 4, I get B, which is mu naught. N by 2 pi r is small n, mu naught n I. This is the magnetic. B is mu naught n I. We're getting the same expression, but remember this 2 pi r is the average length. See, this is like if you have system of this system, then this is the inner length, this is the outer length. The average length will lie some between here. So I'm taking this as the average length, 2 pi r, which is where r is a plus b. Now let's calculate in region 3. Region 3. So let's take an imperial loop here. So this is the imperial loop. So Minashi, what is the radius of the imperial loop? It's greater than b, less than b. What is the radius?
Greater than B.
Greater than b will be the radius of the imperial loop. So we consider an imperial loop of radius r greater than b. We consider an imperial loop of radius r is greater than b. I need I enclosed. See, if you see I enclosed, see, this is your loop. These are n turns. This n turns, and current is coming outwards. So if I take outwards current as positive, then your I enclosed is Ni minus. Like see this cross. Again n turns. Now the current is going inwards. So if I'm taking outwards current as positive, then I should take this inwards current as negative. Then this is Ni minus Ni. And what is Ni minus Ni? That is 0. Now if I enclosed is 0, that means magnetic field in third region is 0. So the whole magnetic field is confined only within the core. Only in this region you will get magnetic field. 0 magnetic field here, 0 magnetic field here. So you can write that magnetic field is confined only within the core. Note it down. That was about Toroid.
So this
Yes.
functions similar to solenoid.
Yes,
It
it's also
is-
similar to Solenoid. Both generates magnetic fields. Tell me if
So
you have written.
solenoid, there'll be magnetic field inside the coil as well as outside, right, sir?
Sorry.
In a solenoid, inside the coil also there'll be magnetic field, right?
Yes, outside is also magnetic field, but the strength of magnetic field is weak as compared to the one inside. But if you take a toroid, then outside it's absolutely 0. If you take toroid, then magnetic field is only within the core. Everywhere else it's zero. Can I scroll it now?
Yes, sir.
Nabil Khan, doubt in any step?
No, sir.
Raj?
Sir, I'm doing so.
Sorry?
Sir, after equation, substituting equation 3 in 1,
Uh,
we found magnetic field in region 2, sir. And why
yes.
again we found magnetic field in region 2 as mu 0 and 9.
Okay, this is the exact expression. Now we want to relate this with that of solenoid. That's why we extend these calculations. We can stop here only, but we just want to extend this calculation to compare it with mu naught and I. That's why I did this. Naraj, you were saying something. You have doubts or no? Everything is fine.
No, sir. Saying just can you scroll up a bit?
Yes, yes, yes. This much or more?
Yes, sir, just this one.
Sir, for region 1, we directly said that I enclosed is equal to 0 since there
Yes.
is no wire inside.
There was no wire
Oh.
inside.
For region 3 also, can we say the same thing?
No, because there are wires inside, no? See, this is region 3. So these wires are inside region 3. These wires are also region 3. But the thing is, the current which is coming outwards and the current that is going inwards are equal. That's why our net current is.
Yes, sir. Then, sir, in the region 2 also, current will go inward and outward same rate, right?
Hmm?
In current in region 2, that is also inside solenoid, right?
Yes, but if you take region 2, see, if you take this region 2, only this current is enclosed, which is going inwards. Not both the currents.
Yes, sir. Sir, in our textbook, NCRT,
Which
for
one?
Ampere's circuital law in the textbook, it's been given like 2 pages worth of notes. Sir. Like they've also given some points regarding validity and some things. Is it necessary to do all that? Or?
Points regarding what?
Ampere's circuital law. Sir. 1 minute, I'll just bring the textbook.
Hmm. Yes, everyone have written up to here.
1 minute, sir.
Sir, it says like the above result for infinite wire is interesting from several points of view. It implies that when the field at every point on a circle of radius r with the wire along the axis is same in magnitude, in other words, magnetic field possesses what is called a cylindrical symmetry. The field that can normally depend on 3 coordinates depends only on one r. Wherever there is symmetry, the solution simplifies.
Yeah,
And
this is what we have discussed in approximations for an imperial loop. These are different words of saying the same thing.
yes,
The
sir.
simplification he's talking about is magnetic field is either parallel or perpendicular, and magnetic field is uniform. That's the same thing that we have discussed.
Yes, sir.
And cylindrical symmetry simply means your magnetic field is in the form of circle around the cylinder. That's why I told you to take an imperial. For a particular point, magnetic field will be tangential, length element will also be tangential, angle will be 0. That's the same thing that these points means all those points that we wrote for this imperial loop. That's it.
सर एक बार डायग्राम दिखा दो.
And sir, also in
Yes, sir.
chapter 1, for continuous charge distribution, they've given some formulas. Delta E is equal to 1 by 4 pi epsilon 0 rho into delta V by r dash square into r dash cap. And E is approximately equal to 1 by 4 pi epsilon 0 into summation for all delta V rho delta V by r dash square into r dash cap. Sir, what does that mean, sir?
That's nothing. That's the superposition principle only. See, the charge density Q rho is Q by V, right? So you can write your Q as rho V. Fine. When you apply superposition principle, you say that force is vector sum of individual forces. And the expression of force is it's K Q1 Q2 by R minus R2 minus R1 ka cube into R2 minus R. So it's just applying the vector summation only. We can discuss it at the end of the class, Nabila. Otherwise, others will feel like
Yes, sir.
wasting the time. We can discuss it at the end of the class. Okay, so that toroid is over. Okay, do this question. Question number 57. This one. Note down this question and tell me the final answer.
Sir, by inside the solenoid, you mean inside the coil or inside the circle?
Inside the circle. This way.
Like in region 1 or?
Yeah, it's solenoid, not the toroid.
Okay, sir.
Answers. Yashika, answer.
Sir, what is G, sir, in the questions?
Gauss, CGS unit. Does anyone get answer?
Sir, mine
Akshay.
is not matching with the options.
Okay. Akshay, Anshika, Noah.
Sir, how to get in Gauss?
Gauss, you just do your calculations in Tesla, then multiply it with 10 raised power 4. 1 Tesla is 10 raised power 4. Gauss. Okay, no one is getting the answer. Let's do it together. We need magnetic field inside the solenoid. So, Minashi, what is the expression for magnetic field inside the solenoid? Which expression will use? Sorry?
Mu 10 into I.
Mu naught and I. Mu naught is given, it's 4 pi into 10 raised power minus 7. I is given 6 ampere. The whole issue is with this n. What is small n, Saifullah?
Number of turns.
It's not number of turns. No. Nabil Khan, what is small n? Number of turns or something else?
Number of turns per unit length.
Per unit length. Number of turns per unit length means total number of turns divided by length. Now, Read this statement. 90 centimeter long solenoid means length of the solenoid. 6 layers of windings of 450 turns each. It's not number of turns per unit length, it's total number of turns. 450 turns of 6 layers of winding.
Into 6.
Yes, so N is 6 into 450. L is 90 into 10 raised to the power minus 2. This will cancel this thing. 9 5s are 45. So this is 30 into 10 raised to the power 2. This is 3000 tons per meter. That's small. Okay, Nabil, let's check. So we get small n also. Huh? Let's substitute all values here. So your B will comes out to be mu naught, which is 4 pi into 10 raised to the power minus 7 into small n is this 3000 into I is 6. So it comes out to be 4 is a 12, 12 6 is 72, 72 pi into 10 raised to the power minus 7 plus 3 minus 4 Tesla. Or you can, to convert this in Gauss, just multiply this with 10 raised to the power 4. So when you multiply it with 10 raised power 4, 72 pi Gauss. So 72 pi Gauss. Is it clear, Arpit, Miraj?
Yes, sir.
Good. Yes, written everyone? Unib, Noma.
Yes, sir.
Yes, sir.
So this Ampere circuital law is also finished. The next topic is Lorentz force. Sahil, are you still in class?
Yes, I'm here.
Okay. So from here you can follow. This is a fresh topic. So Lorentz force means if you place a charged particle in a magnetic field, then that charged particle will exert some, or so when a charged particle moves in a magnetic field, the magnetic field exerts some force over the charged particle. The force acting over the charged particle is known as the Lorentz force. So we have two types of Lorentz forces. One is magnetic Lorentz force, means when you have only magnetic field, and another is the Lorentz force, which is in the presence of both electric field as well as magnetic field. So first of all, we will do magnetic Lorentz force. Magnetic Lorentz force means your charged particle is moving in magnetic field, and this charged particle will experience some force. That's magnetic Lorentz force. So as you can see, this is the magnetic field to the right hand side, and the charged particle is moving with some velocity v. When this charged particle move in this magnetic field, the magnetic field will exert some force over the charged particle. That force is known as magnetic Lorentz force. And when we calculate that force is given by this expression. Magnetic Lorentz force is this Q V cross P now. This is the magnetic Lorentz force acting on the charged particle. Just like Coulomb's law and other like Coulomb's law and Biot-Savart's law, we will not derive this expression. We haven't derived Coulomb's law. We not even derived Biot-Savart's law. We will not derive magnetic Lorentz force. They're not a part of syllabus. But we will use this expression. So if a charged particle is moving with a velocity v in a magnetic field, that charged particle will experience a force, and that force is given by this relation qv cross p naught. So due to interaction of magnetic field, the charged particle experience a force. This is the expression. If you take this in the scalar form, if you open the cross product, this will be qvb sine theta. The next is direction of magnetic field. Theta is the angle between velocity and magnetic field. Now, by looking this expression, can you guess the direction of force? What will be the direction of force? See, the force that magnetic force is the cross product of velocity and magnetic field. So the vector that you obtain by the cross product of given vectors is perpendicular to the individual vector. Means this force is perpendicular to both velocity as well as magnetic field. So your magnetic force FB here is perpendicular to V as well as magnetic field. So force is either in inverse direction or in outwards direction. The force should be perpendicular to both V as well as V. So there are two options for the force. Either force will come out of the board, like out of your screen of your laptop or mobile phone, or this force will go inwards into the screen. So whether the force is outwards or inwards, to this we will apply right hand thumb rule. Do one thing, just take your right hand and place your finger in the direction of velocity. Apply right hand thumb rule with me. Place your finger in the direction of velocity, just on your screen, and curl it towards the magnetic field. And tell me, where is your thumb going? It's going into the screen or it's coming out of the screen? Just write in chat room, everyone, please. Place your finger in the direction of velocity and curl it towards the magnetic field. Where is your thumb going? Is it going inwards into the screen of your laptop or mobile phone or desktop, or it's coming outwards? Arpit is getting the right answer. Akshat is getting the wrong answer. Noha is correct. Yashika is correct. What about the rest?
Sir, how do we do that, sir?
Sorry?
How are we supposed to place finger?
See, you place your finger along the velocity, in the direction of velocity. Nabil, it should go inwards along the velocity and curl it towards the magnetic field. It should go into the screen of your notebook. Place your finger along velocity and curl it towards magnetic field. It should go inwards into the plane of your notebook.
Yes, sir, it's inwards.
Saifullah, Minashi,
Yes, sir.
inwards. Sahil,
Yes, sir, inwards.
inverse direction. So the force will act in the inverse direction. So for this force, remember two things. The first one is force is perpendicular to both velocity as well as magnetic field. Second thing, the exact direction is given by right hand thumb. Both velocity and right hand thumb rule. Just place your finger along velocity and curl it towards the magnetic field. Thumb will give direction of force. But instead of a positively charged particle, if you have a negatively charged particle, this direction is for a positively charged one. But instead of positive charge, if you take a particle which is negatively charged, for negative charge particle, direction of force is opposite to the one obtained by right hand thumb. So the direction that you are getting here is for a positively charged particle, inverse direction. But instead of a positive charge, if you have a negatively charged particle, the direction that you will get from right hand thumb rule, just inverse it. The right hand thumb rule is saying that force will be inwards. Just reverse it. The force will be out. Yes, is it clear? For negatively charged particle, direction is exactly opposite to the one you obtained through from right hand thumb.
Sir, it will be dot, right, sir?
It will be dot, yes. Sorry, yes, it will be dot. Out. Note it down. Four more, Noha. Can I scroll it? Nabil Khan, any doubt in Lorentz force? Nabil Khan. Yashika,
Yes, sir.
doubt.
No, sir.
Arpit, have you written?
Yes, sir.
Okay. Everyone have written up to here, no?
No, sir.
Yes.
Note it down. Tell me once you have written.
Done, sir.
Okay. Now we have a few 1-1 marker questions from this thing. The first thing is that work done by magnetic Lorentz force is zero. See how we can prove that work done by magnetic Lorentz force is zero. What is the angle between force and velocity, Arpit? If I write this expression that F is Q V cross B, what is the angle between V and F, Arpit? Sorry?
Sir, 90.
90. Since it is cross product, we are getting F by the cross product of velocity and magnetic field. So F is perpendicular to V. Force is perpendicular to velocity. And the velocity of charged particle V is ds over dt also. It's a rate of change of displacement. So if force is perpendicular to velocity, that will mean that force is also perpendicular to displacement. Velocity and displacement are the same thing. So you can say that work done is, it's Fs cos 90. Cos 90 is 0, so you can say that your work done is. So work done by magnetic Lorentz force is 0. If work done is 0, then through work energy theorem, you can say that there is no change in kinetic energy. Work energy theorem says work done is equal to change in kinetic energy. If work done is 0, that means change in kinetic energy is also 0. Which means no change in kinetic energy due to magnetic Lorentz force. No change in kinetic energy due to magnetic force. We can prove it by work energy theorem. Work done is 0, that means change in kinetic energy is 0. What is the formula for kinetic energy, Noah?
Half mv
Half mv square.
So kinetic energy is not changing, that means final and initial kinetic energies are equal. Half m will cancel half m, which means final velocity is equal to initial velocity. No change in magnitude of velocity. Now see, one force is acting over the particle, work done by the force is 0. No change in kinetic energy by this force. No change in magnitude of velocity by this force. Then what exactly this force is doing? Can anyone guess? Work done is 0. Change in kinetic energy is 0. No change in magnitude of velocity. But force is acting over the particle. This force must be doing something. What is this force doing? Yashika, Noha, Nabil Ahmed.
making it revolve.
Making it revolve means it's changing the direction of velocity, right? So magnetic force can only change the direction of velocity. It will not always revolve, but it can change the direction of velocity. So work done by magnetic force is 0. No change in kinetic energy due to this force. No change in magnitude of velocity. It can change only the direction of velocity. Can only change the direction of velocity. Note it down. These are few 1 marker questions on this one. Nabil Khan, any doubt? Nabil is not in class, huh? Naraj? Nabil Khan, are you in class?
Yes, sir.
Naraj, any doubt?
Yeah, no, sir, I'm writing, sir. Can you scroll up a bit?
Yes.
So thank you, sir.
So Nabil Khan is not regular. Anji, can I scroll it? Miraj written?
Sir, just a second. Sir, done.
The next topic is path of charged particle in magnetic field. So we have various cases for this thing. The first case is if charged particle is moving parallel or anti-parallel. So this is the magnetic field and charged particle is moving parallel to field. What is the expression of force on the charged particle? Sahil? Sahil, if charged particle is moving parallel, what is the angle between velocity and magnetic field?
0 degree.
0 degree. And if I calculate force, it comes out to be QVB sine 0. Force comes out to be 0. That means no force on the charged particle. But if it is parallel, anti-parallel, sorry, this is magnetic field. And charged particle is coming in opposite direction. Then how much is the angle between will B and B now? It's 180 degree. Now when we calculate force, the force will comes out to be QVB sine 180. Sine 180 is again 0, so force is again 0. So in both the cases, no force will act on the charged particle. So if no force acts on the charged particle, then it will not change its path. It will continue to move in the same straight line. So if the charged particle is moving parallel or it's moving anti-parallel to magnetic field, then no magnetic force is acting on the charged particle. It will continue to move in same straight line. Path will change if it is moving at some angle other than 0 degree or 180 degree. Just note it down. Then we'll see a few other cases. Yes, can I scroll it?
Yes, sir.
It's okay. Next is charged particle is moving perpendicular, but for the next path, you should know what is centripetal force. For the next part, you should have an idea of centripetal force. Let's discuss centripetal force. So centripetal force is the force required to move on a circular path. So if a body is moving in a circular path, it will require a force. That force is known as centripetal force. So if this is the circular path, a body is moving on this circular path, the mass of the body is m, its velocity is v, the radius is r. It will need a centripetal force, and that centripetal force is given by this relation. It's mv square by r, or you can write this as m omega square r also. Here this omega is the angular velocity. Omega is the angular velocity. The relation between linear and angular velocity is this: v is equal to omega r. So whenever a body tries to move on a circular path, it needs a centripetal force. Direction of this centripetal force is along the radius towards the center. So centripetal force will act along the radius towards the center of the path. This is the direction of centripetal force. If particle is here, then this is the direction of centripetal force. There's one more important thing about centripetal force, that it is a requirement. For circular motion, this force is a requirement, fulfilled by other forces, external forces. So this is a requirement for a circular motion, and this requirement is always fulfilled by external forces. Sometimes the gravitational force which provides the centripetal force, sometimes the electric force that will provide the centripetal force. In our case, it's the magnetic force that will provide the centripetal force. Note it down. I will need an extra class maybe on this Friday. Are you free on Tuesday and Thursday around this at this time, 8:30 to 9:30 on Thursday tomorrow? Or you have classes? Does any one of you have class on Thursday 8:30?
No, sir.
No, sir. No one have class.
Sir, IST.
Yes, IST. 8:30 IST.
Sir, I don't have any class.
You don't have any. No one have any class at that time, na?
Yeah.
I want to keep some maybe for the next 2 weeks. Na, I need some extra classes. So Akshay have. Okay. Akshay, at what time you will finish? You will be free on Thursday and Tuesday?
So Tuesday I don't have any class. Thursday.
So when your class will get over?
9.
9. Yes, we can keep it from 9 also on Tuesday and Thursday. So tentatively, I'm for the next few weeks, I'm want to add 2 more classes. Not 2, 1 will also work. Like we can add 1 class on Thursday. Thursday, 9 p.m. Does anyone have issue with this timings?
No issue, sir.
Okay, let's keep 1 more class. We can just speed up the syllabus a bit. So tomorrow 9 p.m. I will keep this extra class. Okay, these are extra classes. Someday I can cancel it, but I will try to maintain this for the next 2 weeks. So Thursday 9 o'clock will start. It will be a 1 hour or 1 hour 25 minutes class. Okay, time over. So there's the next case. Charge particle is moving perpendicular to field. So if charge particle move perpendicular to field, then path will be circular. We'll do this in the next class. Tomorrow 9 p.m. we will try to finish this topic. Yes, we'll finish it tomorrow. This Lorentz force thing, we'll finish it tomorrow. Okay, so let's leave magnetics at here and start our revision of chapter 3, current electricity. So last time we finished this question number 5. This is the last day when we are doing circuits. Next we will do, today is the last day of circuits. Do this question number 6. You people are making separate notes for this thing, for this JE and NEET thing? Or you're mixing up the notes? Arpit, you're making separate
Yes,
notes
sir.
for this thing.
Yes, sir.
So when you go for your school exams, you can skip this thing that we do for JE and NEET. You can skip these questions also. Write question number 6. See, question number 6 is a direct question. Power is maximum in the circuit when internal and external resistors are equal. If internal and external resistors are equal, then the power is maximum. This is sometimes known as maximum power transfer theorem. Maximum power transfer theorem. Note it down. So in a circuit, the power dissipated is maximum only if internal and external resistors are equal. See, when we're doing current electricity, series and parallel combination of cells, we have written formula for parallel combination of non-identical cells only. Please check your notes. Please check your notes for this formula. We wrote this formula E1 by R1 plus E2 by R2 by 1 by R1 plus 1 by R2 for the series and parallel combination of cells in that topic. Yes. You have notes of current electricity? Akshay, Miraj, Minashi. Does anyone have notes of current electricity?
Yes, sir.
Just check those notes and tell me, did I have mentioned this formula there? Series and parallel combination of cell is the topic. E1 by R1 plus E2 by R2 up to 1 by R1 plus 1 by R2, 1 by Rn. No. Yes or no?
No, sir.
Okay. Okay, let's write. This is not in NCRT, so let's write this formula and start doing the next question.
Sir, the screen is distorted.
Okay. Okay, it's fine now.
Sir.
So write this formula. See, for parallel combination of cells, for parallel combination of cells,
Sir, what was that theorem's name? Maximum power?
transfer theorem. That power dissipated in a circuit is maximum if internal and external resistance are equal. Parallel combination of cells. Say you have these cells, this cell of internal resistance E1, then you have another cell of EMF E2 and internal resistance R2. Then we have another cell of EMF E3 and internal resistance R3. So this is E1, R1, E2, R2, E3, R3. These are the cells. I need equivalent EMF of the cell. So for equivalent EMF, you can either use Kirchhoff law for this problem. But if you want to save your time, you can write your E equivalent as E1 by R1 plus E2 by R2 plus E3 by R3 divided by 1 by R1 plus 1 by R2 plus 1 by R3. This is case 1. But instead of this, if I take this case, this is when all positive terminals are at one side, all negative terminals are at another side. But if this mixing of positive and negative terminals, if this positive and negative terminal gets mixed up, when they mixed up, this is E1, R1, E2, R2, E3, R3. When they mixed up, what we do is we consider one of the polarity as positive, then another become negative. So you can say that your equivalent EMF is E1, this is positive, E2 is negative, and then E3 is positive. And 1 by R equivalent, internal resistance in both the cases is same. Say internal resistance are connected in parallel. 1 by R1 plus 1 by R2 plus 1 by R3. This is not in NCRT. You will not use this formula for your school exams, but you can use this formula to simplify numericals. Just note it down.
I think this formula is there. Sir.
Sorry?
I think this formula is there.
Okay, it was there. Okay, fine. And again, note it down. But this is not a part of school syllabus. Yes. Written.
Yes, sir.
Sure. Now solve this numerical. This one, question number 7. Question number 7 will use this logic. Do it fast. It's 10:12 already. You have just 3 minutes for this question. Answers. Should I solve this question or you people are trying?
No, sir, I'm doing it.
Answers. Okay. Akshay and Noha got few answers. Let me check. Noha is correct. Akshay, you're making some mistake. Okay, time over. I'm solving it. See, you are supposed to calculate potential difference between A and B. Now see, potential difference A and B and potential difference between C and D should be same because no current is passing through this resistor. No current is passing through this resistor as an open circuit. If no current is passing through it, that means there is no voltage drop across it. MEB is correct. So first of all, we can write here that potential difference across AB will be equal to potential difference across CD. Now to calculate potential difference across CD, what we can do is we can do this thing E1 by R1 plus E2 by R2 plus E3 by R3 divided by 1 by R1 plus 1 by R2 plus 1 by R3. So how much is E1? E1 is 1, R1 is 1, E2 is 2, R2 is 1, E3 is 3, R3 is 1, divided by 1 plus 1 by 1 plus 1 by 1. So 3, 4, 5, 6 by 3, it's 2. That's it. This is 2 volt. Is it clear?
Yes, sir.
Sir, how would you get VAB is equal to VCD?
It's because there is no, it's an open circuit. See, this A is an open point, this B is an open point. No current is passing through this resistor. If no current is passing through the resistor, that means no voltage drop across the resistor. So if there is no voltage drop here, so you calculate VA and VB or VC and VD the same thing. There is no voltage drop here. Yes, Nabil, you get this point?
Sir, so we should only calculate for the
CD point only.
so,
Someone else was asking some question.
सर मैं पूछ सर जो
हाँ।
1 ओम की 3 रेजिस्टेंस है वो हमें कैसे पता इंटरनली है?
कुछ भी हो, सेल के साथ जो एक रजिस्टर लगा हुआ है, take that as internal, doesn't matter. Even if it is external, doesn't matter. The circuit. Okay, the type of circuits are almost over. Let's. Okay, now you know how to solve the circuits. Now let's do RC circuits when you have capacitor along with resistor. Yes, everyone have written?
yes, sir.
Now let's move on to the RC circuit. See, RC circuit is not a part of CBSE syllabus. So there are again very small chances of getting questions in JEE mains as well. So RC circuit means if you have a circuit having resistor and capacitor both. So in RC circuits, we have two cases. Case one, which is charging of capacitor. charging of capacitor. So here you have a capacitor. You connect this capacitor to a resistor and you connected this to a cell with a key. The EMF of the cell is. Now, when you switch off the key, you close this key. When you close this key, the current in the circuit starts increasing. The charge on the capacitor starts increasing. The capacitor starts charging. No, sorry, current will not increase, current will decrease, but the charge on the plates of capacitor will keep on increasing. The charge keep on increasing until your capacitor becomes fully charged. When your capacitor becomes fully charged, it will not withdraw any current from the circuit, will not withdraw any charge from the circuit. That means there is no current in the circuit. When the capacitor becomes fully charged, then current in the circuit is zero. So when you write charging of capacitor, you need an equation for charging, that what is the value of charge at each instant. So the equation is this: Q is equal to Q naught 1 minus e to the power minus t by tau. You will not use the derivation of this equation in your mains exams. So I'm not deriving it here. So here, what is Q naught? Q naught is the maximum charge. And Q naught is C into the EMF of the cell. Here E is the EMF of cell. Tau is time constant. And its value is equal to RC. See, this time constant is important for dimensions. Time constant is a time. So the dimensions of this thing is T1. This is the equation of charge. Now, and if you want current here, then current I is just differentiated dq over dt. And you can derive it, comes out to be I naught e to the power minus t by tau. Here I naught again here is the maximum current. And maximum current is nothing but EMF divided by the resistance. EMF by resistance, the maximum current. So when you close the key, the capacitor starts charging. So the charge on the capacitor keeps on increasing. This is the equation of the charging. And the current in the circuit decreases. See, as capacitor keeps on charging, it will, when a capacitor gets fully charged, it will not withdraw any charge from the cell. When the capacitor will not withdraw any charge from the cell, that means current in the circuit will be zero simply. Current will be zero. So current, initially current is very high, then it starts decreasing. And this is the equation of that decreasing current. So you can calculate charge and capacitor at different times, like at t equal to 0. If you put t equal to 0 here, this is, I call this as equation 1. I call this as equation 2. When I put t equal to 0 here, your charge comes out to be Q naught 1 minus e to the power 0. E to the power 0 is 1. So it's Q naught 1 minus 1, which out 0. At t equal to 0, there is no charge. If you calculate current, no charge, no, there is no need of current. If there is no charge, that means your capacitor is behaving. There is no charge here. If you want to calculate current, when your current is I naught e to the power, just put the value of 0 here. E to the power 0 is 1. Your current is I naught, your current is maximum. So at t equal to 0, charge is 0, but current is maximum. That means your capacitor will behave like a short circuit. The capacitor will behave like a short circuit at t equal to 0. If I take another time, like I take t equal to infinite, t equal to infinite means steady state. Steady state means point when your capacitor is fully charged. So when you put t equal to infinite in this equation, you get Q is equal to capital Q 1 minus e to the power minus infinity. What is e to the power minus infinity? That is 1 minus 1 by e to the power infinity. E to the power infinity is infinity only. So that's capital Q 1 minus 1 by infinity. 1 by infinity is 0, so it's capital Q only. So when your capacitor approach steady state, the charge on the capacitor is maximum. And if you calculate current at this point, like instead of this t, you substitute infinite, then this is I naught e to the power minus infinity. E to the power minus infinity is 0. Your current comes out to be 0. Means when your capacitor becomes fully charged, no current will flow through the circuit. Means your capacitor will behave like an open circuit. It's an open circuit. We use this thing in numericals. He will say in numerical that capacitor is in steady state. If capacitor is in steady state, that means no current will pass through the capacitor. Capacitor will behave like an open circuit in at t equal to 0. Then he can ask you to plot graph. This is time and this is charge. So when you increase time, the charge increases. Finally, a time comes when the charge becomes steady state. The charge becomes maximum, Q naught. And then he can ask you to plot current versus time graph. See, initially your current was maximum, I naught. See, at t equal to 0, your current was maximum. But gradually your current decreases, it decreases, and it finally approaches 0. So these two graphs are important. This is charge versus time graph. This is current versus time graph. And again, this topic is not in your syllabus, school syllabus.
Sir,
But-
in the second graph, t will approach 0, it will become completely 0, sir.
The current t will approach 0.
Sir,
It will never become 0. I? Yeah,
Which is-
it will approach 0. At t equal to infinite, it will become 0.
Okay, sir.
Can I scroll it? So we'll use these things in numericals.
Max current means current that flows outside capacitor, or
Sorry, Q max means capacitor is fully charged. The charge on the capacitor is maximum. Similarly, I max means current in the circuit is maximum.
pencil.
Yes, written. So you should remember these results. At t equal to 0, your capacitor behaves like a short circuit. Means you can replace your capacitor by a straight conducting wire. But at t equal to infinite, your capacitor will behave like a short circuit. Means you will replace it, sorry, open circuit. So replace it by the open points. Yes, written?
Yes, sir.
Okay. We'll stop here. In the next class, we'll do numericals. Like we'll search previous year's questions based on this concept. Although there are very few questions which are based on RC circuit, but we do those questions. Okay, we'll stop here. We'll continue this tomorrow, 9 o'clock.
Sir, it will be a 1.5 hour class. As
Uh,
usual.